Yeah, we can start.
Okay, I'm gonna start. I'm looking for my slides.
Yeah, yes, sir.
Share my slides. Okay, let's get started. Okay, I'm going to say. Okay. So the section before, I think that is monolithic. I think if you see this picture, it's getting better. Is that right? Clear? So basically what I show here, I just want to show a section of that monolithic. The real monolithic is I keep on saying you catalytic converter is just like this. Okay. So basically we can coat inside surface, and then so that when microwave come this way, so if microwave come this way, they don't heat the surface. They just go and look for the catalyst. Okay, so the heat. Otherwise, if you heat with the conventional heating, that whole thing will be hot. But microwave basically can heat selectively what catalyst coated. And also it's the thermal imaging is basically this section, the so-called where you see the camera, see this section. Okay, going this way. Anyway, okay, so and also this morning we talk about since we want to use the monolithic, there are three distinct advantages. Is that right? Heat transfer, and also the no pressure drop, and then the what you call let's see the third heat transfer, and also productivity. Productivity means when you coat the catalyst, it's much more efficient than the powder catalyst. So this is what we left from last session. So then I use this cartoon to compare why it's efficient, because most of all the catalysts coated are fully utilized, whereas if you pack the powder, you don't utilize the whole thing because there's some channeling bypass. So before we go to this topic, challenge and solution, plasma water, plasma solid interface, I want to do a quick exercise. So let me see. Let me stop sharing. Let me stop sharing and then.
You can. Sir?
Hello?
Yes, sir. I'm having one question, sir. Actually, morning class we have discussed about the monolithic kind of catalyst. In that you are going to prepare, you have prepared the monolithic kind of catalyst using 3D printer, right, sir?
Okay. I cannot hear your question. Can you speak slowly because there's some echo here. Could you repeat your question again? Go ahead.
Sir, what method you have adapted for preparing the monolith kind of catalyst, sir?
Oh, you mean what method we coat the catalyst on the monolithic surface?
Yes,
is that right?
Yes,
oh, sir. Thank you. Okay, let me stop here. Okay, perfect. That's the document of that. Very good. I like that. Keep on. Next week, we still have 5 sessions to go. Keep on doing this. Just stay asking questions. So yeah, I'm okay. The conventional way is called, I'm going to interpret it, okay? Wash coating. Wash coating. CVD. Anybody understand CVD?
Chemical vapor deposition.
Thank you. Yes. ALD. Atomic layer deposition. Okay. And Now, the most famous one is 3D printing. Okay, 3D printing means you basically you have a 3D nozzle that's holding on the here, and then you can basically in 3D printing you can print this surface. Let's say maybe the out layer like a more catalyst and the interior layer less catalyst because the microwave has a penetration problem, right? Microwave may not be penetrate, so you can code differently because 3D printing you can control. The most conventional way is wash coating. So what's the wash coating? Wash coating means you turn powder into slurry. So essentially you put a powder catalyst in the water and then slurry. Then you dip this the monolithic into slurry, take it out, dry, and then calcite. Then they're bonded. But you need something called binder. So binder basically is more like a glue. So some kind of catalyst. Let's say the remember we talk about the this catalyst. Cesium, ruthenium, this catalyst. It just depends on monolithic you use. It may not be very the adhesion very low. So that means you need some kind of binder or adhesive blend together, and then the coat it on the silicon carbide or onto this catalyst. CVD. So I'm glad you asked the question. CVD vapor, chemical vapor deposition. You have your catalyst, you know and then on the in the sources. So basically you have this. You create a vacuum chamber. So you heat it. Those vacuum, the powder will be vaporized and then landed onto this and the vacuum on inside the pores. ALD is the same thing. ALD just atomic layer deposition. CVD you coat like a thin layer. ALD you can control the cold mono layer. So the different, but 3D printing is different. Again, you can make a slurry powder. So because the 3D printing has to be, you have to print the liquid, all right? So basically it's a slurry, or they can start, let's say they can start from the formula. So this catalyst is cesium, ruthenium. So this is powder. So you can basically make a slurry wash coat, but in 3D printing, you can do the same thing. You make the powder into slurry, and then print it. But not necessary. 3D printing, you can print this formula separately. You can have 3 printer jets. Okay, so you can have you want to have a cesium, ruthenium, zero oxide, all right? So you don't need a powder. You can basically have a cesium solution. Cesium solution, and also the ruthenium solution, the salt. And then you can have, so you have 3 things, and then based on the formulation, you can print it. So it's very powerful. Actually, that's okay. I'm glad you asked the question. That's what we talk about. Did I answer your question?
Yes, sir. Actually, what kind of printer you have used, sir? Like there are different types of 3D printers were available, like a printer and laser printer kind of things. Use it deposition modeling also there. What kind of printer you have adapted, you have utilized for printing that kind monolithic kind of catalysts?
I think that for what we are doing is typically we just do the slurry. We make a slurry, we print it. But there are some printer you can print individually. I just don't know the name. And some printer you can print let's say the ruthenium metal. But in most of the time you dissolve ruthenium into the acid. You print the ruthenium nitrate. But you can have the ruthenium wire and then the melted printed. So that the different printers. I'm not expert in the 3D printing, but we do give this to the or it's called innovation shop, they actually print for you. Then you come test it. Yeah, a different way. So you can charge a printer with a slurry, or you can begin with a solid, and then the key is the printer has to be able to melt it and then print it. Yeah. Okay. Now, since you are asking this, I'm going to go back to the yes. Before I go to the plasma, I'm talking about now. Since we talk about 3D printing catalyst, I want to show you one of the slides I presented yesterday. How when we design catalyst, we 3D print the catalyst into the reactor, not necessarily 3D print on the monolithic structure. We can 3D print on the reactor. I'm going to show you. And by the way, here we are talking about taking this commercial monolithic, we print the catalyst onto it. You can print a monolithic structure and the catalyst all together. So this structure can be printed. Okay. So but that's very complicated because at the end you want this structure is a physical structure, and then but you have active catalyst coated. But if you print the structure at the same time with your catalyst, you need a lot of trial and error. That means when you print it, let's say your catalyst may be stuck in the wall. You never know, right? You want the catalyst inside the wall. So when you print this structure all together with catalyst, you never know where the catalyst landed. But we good to have the structure to begin with, because it's standard structure, then you print the catalyst. So let me show you. Very good question. I really appreciate your question. So I'm going to stop sharing, and then I have another one. During you guys' lunch, I pull out the slides I have. Actually, I lectured yesterday, and then I think I was in a rush. I don't think okay, you see the slides. I'm pretty sure you remember what I said, all right? Yesterday, it's a membrane reactor. Driven by the microwave. We coat catalyst on the surface. Okay, so today I'm going to show you how we monitor the activity when we print the catalyst along the lines of membrane. Remember we want to print some place we put a lot of catalyst, some we put a light catalyst because the microwave. Remember, if you remember yesterday, what I did was I drew something. I forgot which one I used to draw that. Maybe this one. Yeah. So remember this microwave, when they landed on surface, they go like this. All right. Remember yesterday. So that means when we coat catalyst, we want this basically this curve shows intensity. If you turn this microwave, go this way. If you basically the microwave. Oh. So basically the microwave go along the lines. Come on, turn. Yep. Oh. You see the microwave go along. So there's the top, high, low, high, low. That means somewhere along this tube intensity high, sometimes low. That means in order to take advantage of this, so the intensity high, we just put a light active catalyst here. We put more catalyst here. Now the question is how you mount, because obviously when you have more catalyst in here, a light catalyst here, the reaction at different segments, they are different, right? How do you monitor the activity? I think yesterday I left out in here. So today I found the picture. I'm going to show you. I'm pretty sure the audience, when I say how you monitor inside the reactor, one of the students say the in situ the spectroscopy. This in situ spectroscopy we are building. So it's Raman. So basically, this microwave come in. We have Raman in situ spectroscopy. So we have this is the blue line called optic fiber. See, this is the reactor, all right? So this is center the piece the catalyst is mimicking what we have, and then we want to know. see this is the red line. It's a laser. We can move them around and then to see the activity, to monitor ammonia, so the information come back to Raman. The word in situ. The word in situ Raman and means it's really the on-site. That means it's under the temperature, under the pressure, and then we monitor the real-time spectroscopy. Okay, and then to get information on the catalyst structure change and also the activity. And there's another terminology I hope you heard about. It's called operando. It's the same in situ. Operando means real time. If you factor in time, every 10 seconds you take the data, then you know what's going on along the tube of the reactor. So anyway, this is the in situ the Raman spectroscopic we build, and then the reactor chamber, the cavity driven by the microwave, so we can analyze the catalyst and also the ammonia synthesis performance. So any question on this? I'm glad you asked questions since you asked the three. How we call the catalyst. Then we thought about 3D printing. So yeah, so this is another way. After 3D printing, how you monitor the activity. Then you give the information back to the 3D printing shop. Then they can optimize their printer so that you print the more active CAD. You have to give feedback and forth. How to get the feedback information? You have this in situ Raman or operando Raman analysis provide you with data. And then you can do the in situ FTIR, if you ever heard of it, but Raman is more powerful for the microwave reactions. Okay. Any questions here before I move to next?
Yeah, yes, sir. We can move to next.
Okay, no question. Okay. So next will be a quick case study. I think since the I think that I can count on so many students here. You can divide in a 2-people group. If I give you the problem, so we haven't talked about how you measure the ammonia. I'm going to stop sharing. Okay. I'm going to find my case study. This time it's a little bit complicated, unless you are you are a reaction engineer, the major. But on daily basis, we keep on remember the curve we show. Ammonia decomposition, conversion. I show you data. How would you measure the conversion in the laboratory? So first, let me we need to go a quick case study. Hold on. All right, let me share my screen. Can you see my screen now?
Yes.
All right. So this is another case study. Typically, in laboratory, when you do ammonia synthesis, this is what you do. You have a continuous flow, either called microwave-driven reactor or fixed bed reactor, thermally heated. So it all follow the diagram like this. Typically, you feed in hydrogen and the nitrogen, and then at a stoichiometry ratio. You look at the equation. So every time you have 100, let's say you have 100 ml per minute nitrogen, you will have 300 ml per minute the hydrogen. So the flowing through after reaction, you have this so-called ammonia analyzer. That's my question to you. I want to see how many analyzer can do ammonia analysis. But the analyzer give you ammonia concentration, and then you have hydrogen and nitrogen come out. Okay, so let me ask you a question before you can calculate the conversion of N2, because we have to we have to have a very clear definition of what's the meaning of conversion. Okay, so all right, for ammonia analyzer, how many analyzer you are familiar with? Can you name some instrumentation you can analyze ammonia? Anybody knows?
Ammonia sensor is available, sir, to detect the ammonia.
What? Say it again. What's the name of analyzer?
Diode based sensor.
Okay, sensor. Okay, cool. Let's drop down.
So we can detect by gas chromatography.
Yes, thank you. GC, gas chromatograph. Have you ever heard of my?
Yes, we know that.
Yes,
GC.
so you have, yes. FTIR. Okay, all right. You can do this. Yeah. Yeah, there's all kinds of instruments you can analyze ammonia. The key is you want to make sure you analyze ammonia, and sometimes you don't have to analyze hydrogen and nitrogen. As long as you know ammonia, you can calculate conversion. That's the exercise we are going to do next. Now, okay, so now I'm glad you're all familiar with analyzer. You can use either one, GC, mass spectrometer, and also FTIR. Okay, so now, and also another one is you can basically put this ammonia into you can do the pH analysis. All right, so that's old way. 100 years ago, there are no GC, there are no the mass spectrometer, there are no FTIR, but the farmers actually use the ammonia solution. They analyze the ammonia concentration. So they put ammonia in solution. They basically, you can do the titration. You can analyze pH. The different way to do that. Today you can do the so-called pH meter. Then you go through calculation. So okay, I'm glad that the audience does have a knowledge on this. So the good news is ammonia synthesis, nitrogen plus hydrogen, they form ammonia only. You do not produce any other compound. You produce ammonia, then you have nitrogen and hydrogen. Can anyone tell me there's some technology, if you run the plasma, you do have a little bit byproduct formation. But most of ammonia doesn't have.
Yeah. Yes,
That's
sir.
why I keep on asking my students, if you are hydrazine, I think. Anybody have ever heard of this compound?
Yeah.
I think it's called hydrazine. Let me stress about hydrazine. I'm sorry, not hydrazine. So hydrazine, I can tell you it's basically this is the hydrazine. I can tell you when you produce make ammonia using microwave or using thermal, you don't have too much this compound. It's probably ppm level, not very high. So I keep on telling my students, anytime if you see a lot of nitrogen like this and hydrogen like this, we will be very rich. Anybody can tell me what's this compound useful? It's very expensive.
A good address.
Yeah, just somebody just said based on your knowledge or what you heard, nitrogen.
Sir, for nitrogen-based solution, they were commonly used for capturing the CO2 which is coming from the industry.
Yep. So basically, this is the specialty chemicals,
Yes.
and also it's a propellant. Propellant means they can use it as a jet fuel.
Propellant.
Propellant.
Fuel.
Yeah. Yep. So I think there's if you look at I'm talking about the aviation fuel. Aviation fuel, I don't know in India how you name aviation fuel. In the US, it's very popular. They call it JP8. Okay. I think JP8 is still the hydrocarbon base. Okay. But when you get to something called JP, I think it's JP10. JP10 is non-hydrocarbon based. I think it's this is the this is the propellant. So basically, with this you can fly very high, and then the energy content is very high, but it's very difficult to make. So you can do the internet search to see how they make it. But the thing is, you do produce a little bit, but not too much. Just think majority of your product is ammonia. Okay, so that's the yeah. But this is a side story. So I want you to do a quick case study. First, let's define. I want you to, based on this condition, nitrogen 100 ml per minute, hydrogen 300 ml per minute, and then I want you to calculate, and also the analyzer shows the ammonia concentration is 5%. So this analyzer, basically, this analyzer shows 5%. What does it mean? The other 95% are nitrogen and hydrogen together. But you do not need to know nitrogen and hydrogen concentration. All you need to know is the ammonia concentration, and then the flow rate of this. You should be able to calculate the conversion. Let's define the conversion. What's the definition of ammonia conversion? Can anybody tell me the ammonia conversion?
Yes.
So basically, yeah, go ahead.
Actually, volume basis data is provided.
Yeah.
As it mentioned, output gas contains 5% ammonia concentration.
Yes, it's all volume percent. It's all volume percent. Okay. So the conversion also calculate based on what is a volumetric conversion. Yeah. All the mole conversion. Molar conversion and the volumetric are the same. All right. So
yes.
Yeah. So I mean, I want to give you 5 minutes to do the calculation. So but I want to make sure you understand calculate conversion for nitrogen. Nitrogen conversion means you have this much coming in, okay? Nitrogen coming in, you need to know, okay? You need to know basically it's make sense, all right? You have this much inlet, 100 ml per minute, and then you need to know how much. I'm talking about inlet N2 means the inlet N2 flow rate. You need to know. You need to find out how much outlet N2 flow rate, and then the differences divided by inlet. That's your conversion. Make sense, all right? Because this is how much coming in and how much outlet. Whatever the difference is times 100. That's how much you converted. That's in the world of reaction engineering or catalysis. This is the definition of conversion. In minus out divided by in. That's conversion. Make sense?
Yes,
so I will do this. I will give you 5 minutes. I will tell you, give you a hint. You need this 5%. You need this equation because it tells you the stoichiometrically how much you can do, and then you need this the two numbers. Okay, so you need the number here, and you need the equation. Calculate the conversion. I give 5 minutes. Yeah, if you have calculator, but after 5 minutes, I'm going to show you the methodology. But if you can do quick calculation, you can calculate now. Just talk to each other.
Sir, one question, sir.
Yes.
Sir, we have to calculate molar base.
It's okay. So I'm going to change it. It's fine. Let's change it.
Yeah.
So mole, it's the same thing. Volume and the mole is the same.
Okay, molar. So actually,
molar, yeah, it's a 5 mole. Yeah, it's the same thing. Molar.
Yes.
Okay. So the molar is the same. If you, I'm pretty sure you learn physics, all right? So PV e, oh geez, what I'm doing? Hold on. I choose the wrong one. I'm gonna
PV equal.
molar concentration and the volume concentration, they are the same. I separate, okay? So PV equals nRT, all right?
Yes,
So
sir.
this, yeah, this is n the vol. So you have same. If you have a same, the volume percentage is same as the molar percentage, all right? Yeah,
Okay.
yeah. So but I give you the mole percent. Since you're familiar with the mole percent, let's do mole percent. So tell us the calculate the molar conversion of nitrogen. Is that clear now?
Yes, sir. Clear.
Okay,
Sir.
go ahead. I'll give 5 minutes, okay? And you should tell me how you calculate. Yeah. I'll be back in about let's say I need to take some tea to drink. Okay. Yeah, 5 minutes ago, let's go. Okay.
Yes, sir.
So
Yes, sir.
if you don't have a calculator, you want to solve it. I want somebody to describe to you how you calculate based on it.
யாரோட இங்கதான் வருமா லிங்க் ஆமா GIAN. All fields okay.
It's 300. How you could test it 300? It's 300.
Yeah, I think you can talk each other, okay? Make sure you agree each other. I will show you my calculation, but you make sure you agree each other. Let's compare the data. I can tell you, I have a graduate student try to use Aspen to simulate. It doesn't help. You have to calculate by hand.
Hello, sir.
Yeah.
Uh,
How much?
yes, sir.
What's conversion?
Yeah, nitrogen. 1 minute. Sir.
Yeah. Mute பண்ணிட்டேன்.
Hello, sir. Sir,
Yeah.
from my calculation, whether it is correct or not, that I don't know, sir. But I calculated, it's coming around 99.75 nitrogen concentration. I mean, 99.75 nitrogen remains. Remains as nitrogen. Only
Okay.
0.25% alone gets converted into ammonia.
Okay.
So the concentration of nitrogen is 0.5 divided by 0.25. Sorry, 100 minus answer.
Yes, I'm going.
So you need to know. You need to know. You have 100. Basically, you calculate nitrogen. You have 100 mole per minute nitrogen, and after the use of after the reactor, at this point, what's the nitrogen here? That's the key. Then the difference is, yeah. So I'm doing my calculation now. Yeah, you did. I think whoever finished calculation, just tell me that nitrogen flow rate.
7.5%. Ammonia. 45%.
Sir, 24.8 8 volume percentage, sir.
Hold on, I'm going to show you my calculator, okay? So just hold on 1 second, okay?
People. Come on. 24.8. Volume.
So the okay.
Okay. Volume. Why you?
Okay, so anybody can tell me N2 here. What is here? N2. You have, because obviously you have ammonia formation, and then when the 100 will come out, this number should be less than 100. What's this number?
99.5.
No, it's not 99.5. I think you are missing some kind of decimal point. This one. You really need to get this point. What's this one?
Sir, 99.5 mole per minute.
It's non. Did you say 99.5 or you say 90.5?
99.2.
Say it again.
Sir, I have calculated using the material balance equation.
Yes,
So
you have. Yeah.
final product you have we have received as the ammonia concentration is the 5 mole percentage. So remaining gas is 95 mole percentage of the nitrogen and hydrogen.
All right. Okay, hold on.
Yes, sir.
So is that your answer? 90 about 90.5 mole per minute, correct?
Yes,
Did you get this number?
No,
You don't get this number?
we are not getting that, sir.
Okay. You don't get this number, all right? Let's work together. Oh my God. I can tell you, if your concentration here is a 5 mole %, your nitrogen conversion is almost double this. It's around 10% or 9%. So the answer is it should be 9% conversion. So that means the key is this number here. Okay, let me show you the calculation, okay? So let's assume, yeah, I know it's hard for you because I used to, when I teach in every class, it sounds pretty simple, all right? Oh, I 5% more analyzer, and then I give you a number. Very few people come, and then a lot of students try to the program that I say you don't have to program that. You have to make sure you use the Excel or some calculator. It's very simple. I'm going to show you. Okay, hold on. So the key is you want this number, right? Let's assume. I'm glad we do exercise together. Otherwise, remember this morning I talked about ammonia decomposition conversion. I know some students did not understand the conversion. So now I'm really show you, okay? So let's assume. Okay, let's assume X mole of the nitrogen N2 disappeared. Disappear means X mole get converted. You follow me? So X mole of the, so that what does it mean? If passing through here and X mole get converted. Okay, let me put it this way. I small the nitrogen disappeared, how many? If I small the N2 disappeared, or converted.
3x moles.
3x, all right? How many more of ammonia form?
2 mole. 2x.
2x. All right?
Yes.
Okay. So then you need to build you need to build the equation. So what's it, this analyzer tell you? 5%, all right? So analyzer 5, keep in mind, if you have X more nitrogen disappeared, and then the 3x of the 3x of this the what you call that hydrogen disappeared, what you end up with in here? I'm writing here. Yeah, it's very easy to teach in classroom. I don't have to waste my time. So okay. Make sense? Correct? Because X more disappeared. Then you watch and then you begin with 100, X more disappeared, and end with 100x here, this point. Correct? Can anybody say something at this point? I would say outline. At this point, N2 equals 100 minus X, correct?
Yes.
I think, okay,
Yeah.
yes, is that right? Okay. So at this point, okay, the right outline, because you have something converted, and then right outline, you have N2 equals 100 minus X, H2 minus 300 minus X, and then where are those X go? Make sense?
Yes, sir.
Okay, yes, sir. All right, yes, okay. Now, all these 3 components, okay, we need to basically, what I'm going to show you, we need to build the equation, then we solve equation, all right? How do we solve equation? So now you agree, we assume X more disappeared or converted, passing through. So basically this one going here, N2 hydrogen here, they formed, right? And all these 3 things go into the ammonia analyzer. Say, oh, you have 5 more percent. So what does it mean? 5 more percent. No. It's ammonia. All right. This analyzer tell you ammonia concentration in the total gas. What's the total gas? Divided by 2x divided by 100 minus x. This is denominator, okay? Plus, okay, hold on. 300 minus 3x plus 2x. All together, this denominator, okay? See that? 2x divided by all these guys together. Equal to 5%. Can you solve this equation? X. You have one variable, you build the equation. Does it make sense?
Yeah.
Can anyone solve it? Give a try. I will give you another 5 minutes. So we have 10 minutes, we have 8 minutes to go. Just see the answer. See if we can get my answer. Basic N2 here, yeah. Solve the X. Tell me what's the X.
X value.
basically 2x divided by everything here adding together, N2 plus hydrogen plus ammonia equals 0.05, 5%, all right? So just solve this equation, pretty simple.
Sir, X value is 9.5.
Thank you, that's it. Okay, now X is 9.5, do it again. See what's the conversion? See this is the definition? You inlet 100, you outlet how much? 90.5, all right?
Yes, sir.
What's the conversion?
Actually, we need to calculate the nitrogen molar concentration.
Why
So,
you need to calculate molar concentration?
Yeah, we know that that is 90.5 in volume percentage. So we have to convert that into volume. In
No,
flow.
I give you more percent. See the data, I give you more percent.
Yeah, yes, sir. We can calculate it.
Yeah, just you already get on. You get a 9.52. That's a more percent. That's not volume percent. I already changed it. That's why I say the more percent, the volume percent, they are the same. I mean, if you in terms of that's why PV equals nRT.
Yes.
It's the same. So I already corrected. I already give you the more percent. So you say the 9.52 is right X. So the outlet is how much? It's basically 100 minus 9.52 is 90.5. All right? Is that right? N2?
Yeah. Yes, sir.
So what's the conversion? N2 conversion. Basically, it's a see this formula. The 100 minus leftover 90.5 divided by 100. All right? Make sense? It's 9.5% the conversion.
9.5. 90.
9.5 conversion. I'm talking about conversion.
Is
that right? Conversion 9.5%. Everyone agree? Is that right? Conversion, the definition of conversion is inland.
90.5.
No, it's not 90.5. 9.5. So basically, it's inlet nitrogen minus outlet outlet nitrogen, and then divided by inlet.
9.5. Yes, sir.
Yeah, 9.5. All right. Okay.
Yes.
So what do you learn here? I think the reason I ask you to exercise, my students in my laboratory, they gain a lot of experience. Every time when you see 5% conversion, 3% conversion, you double the number, that's your conversion. Follow me? So provided you have to run stoichiometry. Stoichiometry means at the inlet, your nitrogen and hydrogen always follow the 1, 2, 3. What does it mean? When you follow 1, 2, 3, every time analyzer tell you 5%, 10%, you know you just times 2 roughly. You know that how much nitrogen disappeared. That's the rule of thumb. Okay. But if you change the ratio, that's a different story. So basically, that's every time my students tell me, I say, because it is conversion that's important, not concentration. Ammonia concentration, one thing, but you want to know how much nitrogen disappeared from the after passing the reactor. So the rule of thumb is the moment you have an analyzer, and then you run 1 to 3 ratio, the moment analyzer say 5%, you double it, that's your roughly that's your conversion. See, 5%, 9.5%. 5% concentration translate to 9.5% of ammonia conversion. So that means if you have 100 more ammonia come in, and then roughly the 10 more is gone. It is true because 100 come in, you end up with 9.5 more. Roughly 10 mole. Okay, so it's a conversion. Conversion is simply double ammonia concentration. Make sense?
Yes, sir. Clear, sir.
Yeah. I'm glad we do this exercise because now you understand, it's for such simple reaction, even conversion takes a little while to understand. Yeah, it's very important. So that's why this morning I show you ammonia decomposition conversion is actually a reverse reaction calculation. There's a lot of work. You have to really make sure you build an Excel spreadsheet when you get, otherwise this analyzer tell you one thing, and then it's up to you to do the calculation, because you can remember we listed so many analyzers, GC, mass spec, FTIR, or pH meter. Those just give you one number, but it's up to you to do all this, I would say the mass balance calculation. Okay. All right. So I think it's a very good exercise. And then I think we take a 30 minutes. You want to take a 30 minutes break, all right? Then we come back. Let's talk about the plasma at the interface. Okay. All right.
Yes, sir.
All right. Thank you, everyone. So I'm glad we went through this exercise. I knew, tell the truth, by
Yes.
just listen to the audience, I knew a lot of students, you are not familiar with this calculation, because it's easy for me, but I found that it's probably a little difficult for you. Okay. I'm glad you understand. Okay. See you in 30 minutes. Okay. After 30 minutes, we come back again.
Yes, sir. After break, we will meet, sir. Yeah.
Say it again.
After break, we will meet, sir.
Okay.
Yeah.
Yep. Okay.
Thank you, sir.